everyone, and welcome to the series of videos on the applications of differential equations. Before we go jumping into this exercise, there are a couple of ideas that we need to go over, namely the two that are on screen presently, so Newton's law of cooling and also for radioactive decay. So for Newton's law of cooling, the rate at which a body cools is proportional to the difference between its temperature and the temperature of its immediate surroundings. So what this means is that the rate of change of the temperature with respect to time, so dt. Notice I'm using uppercase T for temperature and lowercase t for time. That's proportional to the difference between its temperature, T, and the temperature of its surroundings, which we'll call TE, or the temperature of the environment. So what that means then, if it's proportional, is that dt is equal to some multiple of T minus TE. And to show that it's cooling, I'm going to just put a negative in front of the K. So that forces that condition, and that will become apparent in one of the later videos when we actually get to solving the DE. Now, as for radioactive decay, the rate at which a radioactive substance decays is proportional to the mass of the substance remaining. Not going to worry about writing out the differential equation for this one, as the problems that we're going to encounter are going to be a little bit more complicated than this, but that's the general gist of what's going on. So to get into this example here, the population of a city P at time t years increases at a rate proportional to the population at that time. Construct and solve the differential equation and sketch the population time graph. Okay, so we're told the population increases at a rate proportional to the population. So that means the rate of change of the population, so dp dt, is proportional to, and then it's just proportional to the population at some time t, so it would just say it's proportional to p. That means that dp dt is equal to k times p. And notice here that k is positive, which is indicating that it's going to be increasing, or, well, we can assume k is going to be positive here anyway. So now I need to solve this DE. So it doesn't make much sense to anti-differentiate this with respect to t. So what I'm going to do is flip both sides of the equation to get dt dp is 1 over kp. And now I'll anti-differentiate with respect to p. So t equals the antiderivative of 1 over kp dp. Notice I can take the 1 over k out the front, and that will leave me with something that's going to become a log. So t equals 1 over k out front of 1 over p dp. And so that means t equals 1 on k log e of p. And then can't forget the plus c on the end of it either. So the thing here is that this answer in itself isn't all that useful to us, because it's telling us what the time is given to some population. We probably want that the other way around for it to really make sense. So I'm just going to rearrange it. So subtract c from both sides and multiply by k. I'm going to get log e of p equals k at the front of t minus c, and then raise both sides with e to the power of, so we're going to get p equals e to the power of k times t minus c. There's probably just one more thing to do here, and that would be to say that p is equal to ae to the power of kt. And we can do that because this line here could be broken down into p equals e to the kt times e to the negative kc. So just using the index laws, we would know that we could add those two powers together and arrive at the same thing as we had. And the thing is that this e to the power of negative kc, well, that's just going to be some constant, and so we're just calling that a. So I'll say where a equals e to the power of negative kc. And I think that'll about do it. Now the other part of this question though is to sketch the population time graph. So just set up the axes here. So we have population. Oh, please excuse my horizontal axis, that's awful, against time. And well, from here we can see that it's going to have a y-intercept of a, and it's an exponential graph, so we know it would go roughly like this, and then it's going to increase exponentially. It's going to go up quite quickly like that. And that's about all that we really need to do for it. So yeah, I'll leave that video there, and we'll pick up with a couple of other examples in the next one, where we actually look at Newton's law of cooling. So we'll see how that's applied then. See you.